and welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm finding out why Microchip is reliable GNSS. I'm joined by Evan Alexander. Evan is the Senior Product Marketing Engineer at Microchip. Welcome to the podcast, Evan.
Hey, thanks for having me on the podcast, Mike.
It's great to have you on. Can you tell us a little bit about your role at Microchip?
Absolutely. So I work as a product marketing engineer for Microchip's frequency and time systems business unit. And so in our BU, product marketing is kind of a catch-all term. I get to be involved in many of the functional areas of our business, which is great. Right now, I'm the product manager for several commercial product lines, including our frequency distribution systems and PCIe timing cards. I also get to work with our engineering teams on new product development and R&D efforts, which is really fun. I get to do some classical product marketing with talking to customers and trying to understand the market and product fit and kind of developing our product position and how we communicate our value to customers. I get to lead some outbound marketing campaigns, and sometimes I even get my hands a little dirty with some business development and sales efforts. So I enjoy the broad range of activities that I'm involved in, and it's quite a lot of fun.
Sounds like you've got a lot to do there, Evan. And I'm particularly pleased to hear that, one of your roles is really understanding the market. Today, we're talking about GNSS or sat-nav, I guess people would call it, and all about how timing is important. So can you start by explaining why timing is so important in these satellite navigation systems?
Absolutely. So at Microchip, we're big believers that precise timing is a critical infrastructure, and it enables many of today's technologies to work so well, including the Global Navigation Satellite System, or GNSS. I think most people know that GNSS satellites will tell you where you're at. That's how Google Maps works when you get into your car and you put in the location you want to go, and it kind of tells you how to get there. Behind the scenes, it's really precise timing that enables that to work so well. Each GNSS satellite continuously transmits signals that contain two things: a precise timestamp and a location, meaning that the signal tells you what time it was and where the satellite was when the signal was sent. And when that signal on the other end is received, typically by a GNSS receiver, the receiver timestamps when the signal was received, and you can calculate your distance to the satellite using a pretty simple equation. It's going to be the speed of light times the difference between when the signal was sent and when you received it, also called the time delay. And so if you can receive that information from 4 satellites, you can actually calculate your 3-dimensional latitude, longitude, and altitude, or your position. And you can use that to navigate. You can also use the timing information in the signal as your primary source of time. So many systems use that in order to stay synchronized. They receive their time from GNSS and they're able to pass that information throughout a system. So you can imagine that signals traveling at the speed of light need to be very precise. Small errors, even a few microseconds, could lead to hundreds of meters of position error. So in a really very real sense, GNSS is actually mostly about time. And many of our critical industries and markets depend on it. They use it as their primary source of time, whether it's telecommunications or power grids, data centers, financial markets. They all rely on the precise timing that GNSS gives you.
And that's interesting. I mean, we're going to go and talk about how that timing has to be super precise in the equipment that receives the signal. But Microchip does a lot of timing products. Are any of Microchip's products used in the actual infrastructure itself for GNSS?
Absolutely. Some of the satellites themselves use Microchip atomic clocks and crystal oscillators and frequency references on the satellites. And then Microchip also makes systems and technology that receive the GNSS signal and distribute that throughout a system. So many of the big telecom companies and operators will use some of our packet timing systems to receive the GNSS signal and distribute that out throughout a network. So we're kind of involved throughout the entire chain, from the satellite itself to the user side of it that's receiving that signal and distributing that information.
So that's great. You obviously, as a company, Microchip, are really heavily invested in the system and providing a lot of it. Let's now dig into this problem about reliable GNSS. So, I mean, I've got GNSS on my phone. It seems to be pretty good. What is the problem that causes this unreliability, and what are you trying to solve for?
Absolutely. So first off, GNSS is an amazing technology. It has nearly worldwide coverage, and it's free to use. It's used in phones and almost every piece of equipment you can think about. But the signal itself is actually really weak. I think the number is it's something like 1 billion times weaker than your average cell phone signal. And so what this leads to is sometimes the signal can be interfered with, whether it's unintentionally or sometimes intentionally by someone looking to cause problems. And so we call that jamming and spoofing. Jamming being when someone transmits a signal that just overpowers, just is stronger than the GNSS signal, and so it blocks it. And spoofing is when someone transmits a signal that looks like a GNSS signal. It's like a copy of it, but it gives you the wrong information. It may give you incorrect position or time data, and that could lead to quite a lot of issues. You can imagine maybe a ship that's using GNSS to navigate, and if it's getting the wrong information on where it is, it may run on shore. So this is something that's happening more and more frequently today, and it's quite a large problem that many people, including Microchip, are investing in trying to solve.
And that's interesting. I mean, you talk about these two things. I mean, spoofing sounds like that's got to be deliberate, right? That's somebody trying to disrupt GNSS. And then jamming, maybe that's something that could be accidental interference. I mean, can you talk a little bit more about when these phenomena happen?
Absolutely. It often happens in military, in kind of areas of conflict around the world. Many military systems rely on GNSS for navigation. Ships, planes, tanks, they all use GNSS to figure out where they're at and what time it is. And what happens is, because it's so easy to jam or spoof, sometimes bad actors or adversaries, they'll just jam the signal because they know it makes things harder for their opponent. In commercial industries, losing GNSS can happen for a variety of reasons. Often it's unintentionally. Someone's transmitting a signal that they're not realizing is blocking GNSS. It can also happen in urban areas that are dense. So like tall buildings can sometimes lead to blocking satellites and different multipath effects. If you go into a tunnel, you're probably going to lose your GNSS signal. So there's different ways that jamming and spoofing could occur, but at the end of the day, it's a big problem, and we want to have a solution for how can you maintain your system's expected performance when you don't have access to the signal.
And it sounds like these problems can happen in quite a wide range of situations, not just in a conflict. So presumably there's quite a lot of applications that really care about overcoming jamming and spoofing.
That's right. Some big ones for power grids. Power uses GNSS to maintain phase alignment in power distribution, and so you wouldn't want to lose power. That would be a big one. Financial markets use GNSS in order to timestamp transactions, to keep a record of who owned which stock or equity at what point in time, and when ownership changed hands. And so that financial market would absolutely want to be able to maintain accurate timing when GNSS is not available. And they're actually required to, oftentimes, by governments to maintain a certain degree of timing in when GNSS is not available. So it's a big problem, and it applies to a wide range of industries.
So Microchip has a product called a disciplined oscillator to solve this problem. I mean, I know what an oscillator is, but can you explain what the difference between an oscillator and a disciplined oscillator is?
So a discipline oscillator provides what's called holdover timing, meaning it's able to maintain accurate time even when GNSS is not available. Having something that can do this holdover timing is extremely important because that's what allows your system to keep operating normally for an extended period of time while you don't have GNSS. And the idea is that you'll hopefully reacquire GNSS before whatever your holdover source is, before it drifts too much. And so the disciplining aspect is really the magic that makes it a GNSS discipline oscillator more than just a receiver. So inside a discipline oscillator, you're going to have what's called a local oscillator. This could be a OCXO or an atomic clock. And typically this oscillator has whatever performance characteristics your application requires. So if you have a radar system, you probably care about phase noise in order to have better target detection and tracking. And so you would have a local oscillator that has great phase noise performance. Most local oscillators have really good stability over short periods of time, but over long periods of time, they drift. It's just kind of an inherent thing that happens. And so what disciplining does is it compares that local oscillator to the timing signal coming from GNSS satellites, which are tied to atomic clocks that have really good long-term stability. And then using a feedback loop, this could be, sometimes it's a phase lock loop, sometimes it's some sort of control algorithm. It slowly adjusts that local oscillator to stay in sync with GNSS. So you can think of it like, it's like tuning a musical instrument, where the GNSS is the tuning fork and the oscillator would be like a guitar string, where you're not yanking it around, but you're kind of gently guiding it to stay on pitch or on frequency. And so what you get is you get a system that kind of combines the best of both worlds. You get short-term stability with the local oscillator, you get long-term accuracy with GNSS. And so this allows you to hold accurate time for hours, sometimes days, if you lose GNSS. And what you get out is you get out stable timing signals that downstream systems can use. So it's usually a 1 pulse per second or a 10 megahertz signal, but it could be other frequencies as well that downstream systems can make use of.
I mean, that's really interesting. I totally understand that. It's locking to the satellite signal, which is super accurate where it can see it, but it's keeping pretty close to that if it loses the satellite signal. You mentioned the oscillator and you talked about atomic clocks. I mean, that sounds like the key component in a disciplined oscillator module. So Microchip makes these devices, don't they? Is that a benefit?
That's right. So Microchip was the first company to develop a commercial chip scale atomic clock, which most people know of as the CSAC, chip scale atomic clock. We still sell this product today. And of course, since we released it decades ago, we've made improvements along the way. In fact, a new version came out a couple months ago called the LN CSAC, or the low noise CSAC, which has pretty impressive phase noise performance for an atomic clock. The other atomic clock we tend to use on these GNSS TO products is our rubidium-based miniature atomic clock, or MAC. It actually has better long-term stability than the CSAC, but it's larger and requires more power. So it's a classic trade-off a designer would need to evaluate, is the size, weight, and performance. But Microchip's been making these products for decades. And we don't just make the atomic clocks, we make the crystal oscillators too. The OCXOs, the TCXOs, and that local oscillator category is probably the most critical component of a discipline oscillator module. It's going to determine your performance, and it's going to determine which module you'll choose for your system. It's going to be based on that local oscillator.
So it's interesting. And obviously, I mean, I know a little bit about atomic clocks because we've talked about them in Microchip Is before, but presumably your customers can also buy a Microchip atomic clock and make a disciplined oscillator. Is there anything Microchip can do to make your disciplined oscillators even better because you understand to such a depth those atomic clocks?
Yeah, that's right. Anyone could, of course, design their own discipline oscillator, but kind of what we provide in our standard off-the-shelf products is it's a complete system. It's easy to integrate, and it takes advantage of our decades of experience developing and manufacturing these atomic clocks and crystal oscillators. What you also get is you get access to some of the algorithms that we've developed. So these products come with different algorithms that do holdover, disciplining, oscillator aging compensation. We have environmental compensation algorithms like temperature and pressure. And so those are algorithms we've refined over the years. And then we also work with customers. What we often find is for a customer's application, they may look at our standard off the shelf products and need it customized in some way, whether that's they want more outputs or maybe some sort of custom enclosure, or they need a really unique frequency. And so we work with customers kind of tweaking our off the shelf products or even doing a completely new design to fit their application. So yeah, you could design one on your own. It's definitely going to take significant time and effort to figure out what you need. And so it's probably much easier to just work with our team. You know you're getting a high quality product and you get the support of the team. You can ask us questions. You have a team of effort that has centuries of combined experience working on these types of systems. And so we really like working closely with customers. And so our recommendation is, well, just come work with us. Take our product, integrate it into your system. It's going to be a win for both of us.
That sounds great. And I love the way we're ending on support, which always seems to be a bit of a theme of these Microchip Is interviews. I mean, we seem to have covered an awful lot about the whole GNSS system all the way through to the microchip disciplined oscillator products. I mean, is there one thing you'd say to kind of sum up what's most important and the thing people should remember about microchip and GNSS?
Yeah, when it comes to a GNSS DO, as I've mentioned, it's kind of an area of expertise for us. The combination of an oscillator and a reference in some sort of small form factor or really any form factor timing system, that's kind of our bread and butter. We're continuously investing in this product category. In fact, we've just released some new GNSS discipline oscillator products. So I think it's important to remember as you're designing your timing subsystem or the timing part of your system, take a look at our products. If you have questions, reach out to our team. We like working with customers and we are the timing experts and we want to be able to share that expertise and help customers be successful.
I love that. That's so positive. Evan, it's been fascinating. I've loved talking to you. Before I let you go, there's a question we always like to ask. Can you give our listeners an engineering tip or bit of engineering advice?
Oh yeah, sure. Let's see. I think my advice would be make sure you understand your application's timing requirements. And if you're going to use a disciplined oscillator, let's say, you want to match the performance of that local oscillator to those timing requirements. So if you need an oscillator that, say, has good holdover characteristics, make sure you understand what level of holdover you need. And this is going to help you determine whether you're going to need an OCXO, maybe a CSAC or a MAC. And if you have questions or unsure, again, you can reach out to us. We deal with this stuff all day long, and we understand the trade-offs between holdover and frequency stability and phase noise, and we know these products well. So if you're unsure, just call us.
That's awesome. Thanks, Evan. I mean, I'm sure people listening to this, if they're designing systems for taking timing from GNSS, maybe it's for a defense system or maybe it's for telecoms or something like that, they might have questions. If they want to reach out to you, what's the best way to do that, Evan?
Yeah, sure. So you can reach out to me on LinkedIn. My LinkedIn's Evan Alexander, or you can send me an email if you want. My email's evan.alexander@microchip.com. Pretty easy. And yeah, I'm happy to talk to anyone about microchip or timing, or I'd love to hear about your application and what you're looking at. So whatever it is, don't be afraid to reach out. And I'm happy to talk and help out where I can.
That's awesome. I'm sure people will really appreciate that. Evan, it's been great talking to you about GNSS and how disciplined oscillators can make the systems reliable. Thanks so much for being a guest on the Microchip Is podcast.
Thank you very much, Mike. It's been a pleasure.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.